Alright guys, so this week we are going to be talking about domains, to begin the week anyways, and I'd like to review a little bit about what we did at the beginning of the year with domains. So first, domain and range. First, graphically. So when we think of the domain, we think of the set of all possible x's for a function, or for that a function is defined upon, right? So let's say we're given this particular f of x here, and we want to find the domain of it. We'd say, well, you know, there is going to be an x over here at 5, and an x over here at 4, and so on. And so I told you if we could take each one of these points and kind of push them down onto the x-axis, and then look, where is the x-axis shaded in? Now, if this has arrows going in both directions, and you were to push these points down onto the x-axis and these points up onto the x-axis, the domain of this particular f of x would be all real numbers. So we could just use that capital R symbol for the domain. Now the range, we're looking for the set of all possible y values. So we take each one of these points, instead of pushing them down on the x-axis, domain axis, we can push them sideways onto the y-axis and look at, okay, well, where would this y-axis be shaded in if we pushed all of those points to shade in points on the y-axis? This would be y is less than 3. Right? And so the domain here for this particular f is all reals, and range is reals less than 3. Okay? This one here, let's say this point goes up to the value 1. Call this g of x. These dashed lines represent asymptotes, and we would say that the domain of g is going to be all reals except for, takeaway, looks like -2 and +2. Alright? And then for the range of g, we would have things greater than 0 as we push these values across and these values across. Then we would have this little empty space, and we would have things below -1. So we could say 0 to infinity, union that with -infinity to -1. Let me switch those around, because normally we like to have the interval below to the left. So this would be -infinity to -1, union 0 to infinity. And so that would be the range of g. Okay? So we did do domain and ranges graphically, much like this in the fall. And then we also did them algebraically. So when we found domains algebraically, we began by assuming that the domain is all reals, and then we started to remove values. We started to look out for things, right? Many functions have a domain of all reals, but there was 2 cases in particular that would cause our domain to not be all reals, that would give us exceptions to the rule. And the first one was denominators. Denominators are not allowed to be equal to 0. Cannot divide by 0. And so in this first case, we see that x is not going to be able to be equal to -5. So the domain of this particular f was all reals except for -5. All right? To find the range, we would switch, we would solve it for x, and then take a look at what y couldn't be. I'm not going to do that right here. I'm just concentrating on the domains for now, algebraically. But if you rearrange the equation and write x in terms of y, you can tell what the range, what y can and can't be. Finally, we also had to worry about radicals, because the stuff underneath the radical must be greater than or equal to 0. You cannot take the square root of a negative number. It would bring us into the complex plane, and for our purposes, functions right now are only applying to real numbers, that we're really only concerned with real valued functions. So we would say x minus 4 here, the stuff underneath the radical, must be greater than or equal to 0. Therefore, x must be greater than or equal to 4. So the domain of this particular f, we could say, is 4 to infinity. Okay? Now, with these new functions that we've been working with last week called logarithms, this inverse of exponentials, we now have a new problem when we try and find the domains of functions. So we know that, let's say, f of x equals a log base 2 of x. Well, that would mean its inverse, of course, is 2 to the x. And sketching that graph right here, we know the graph looks like this. Its domain is all reals, and its range is reals greater than 0, which means that for f of x, the domain of f of x has to be equal to the range of its inverse, reals greater than 0. And that makes sense, because when we evaluate this f of x, right, the domain comes from saying 2 to the what power equals x, x being my domain. Well, guess what? No matter what exponent we have, x is never going to be equal to a negative number. We can't say 2 to the what equals negative 8. It's impossible. 2 to the what equals 0. Can't do it. We can make 2 close to 0 by plugging in negative exponents, but we can never make it actually equal to 0. So that gives us this new kind of idea that, or this new thing to watch out for in finding domains, that anytime you have a log, we cannot, right? We cannot evaluate a log if what's inside is less than or equal to 0. So our domains for our logs have to be greater than 0, right? And so this is a lot like the radical problem, in that you weren't able to have negatives underneath the radical, but now you also can't have 0. But it's going to be the same idea of solving for a domain. That is, what is the domain of log of x minus 3? Well, guess what? X minus 3 must be greater than 0, so x is greater than 3. You're done with the domain. Okay? Whatever is inside this parenthetical must be greater than 0. And oftentimes we can go ahead and just straight up solve. Subtract 3, you get negative x greater than negative 3, multiply by a negative 1. Make sure you flip the inequality sign. Domain is x is less than 3. When it comes to more complex expressions within the parenthetical, whether that's rational expressions or quadratic expressions, we would say x squared minus 3x minus 10 must be greater than 0, but this is not something we can solve for directly. We would tend to grid it on a number line. How do we grid it? Well, we take that x squared minus 3x minus 10, and because we're looking for where we're greater than 0, we're going to start by saying, okay, where does it equal 0? And it equals 0 at 5 and at negative 2. And so we are going to plot our zeros on the number line. Now here you're not allowed to be equal to 0, so we're going to use open circles or parentheses if you prefer that graphing with interval notation. And then we're going to test some values. So if I plug 0 into this inequality, if I plug 0 into this equality, I get negative 10. If I plug in, I don't know, let's say 6, I'm going to test 6 in here. That's 36 minus 18 minus 10, so the 36 minus 28 is positive. And so I'm going to be positive in this region over here. Look, this expression here is quadratic. It's a polynomial, which means it's defined everywhere, and it doesn't jump or anything like that. And so, you know, the graph of it's actually kind of a parabola, and I'm going to be positive on the outsides, negative in the middle where it dips below the x-axis. And so that kind of helps me with my domain, because I'm looking for where is this expression greater than 0. And when I look at it, I can see it right on the grid. The domain of this log is going to be negative infinity to negative 2. I don't want negative 2 because that's where you're actually equal to 0, and we need to be greater than 0. And then 5 to infinity. All right. So this is how I find domains, and you're going to have some problems this week dealing with the domain of a logarithm. It does not matter what the base is, as long as the base is a positive number, small or big, doesn't matter. We're going to take the numbers inside the parenthetical and set them greater than 0 and solve. Thank you.